Thanks for coming. My name is Dima. I'm not 3 raccoons in a trench coat. I'm sorry if you came for that. You'll be so disappointed. I'm really sorry about it. So what I'm going to talk about is NFC in Android, and specifically I'm going to be talking about like a more complex flavor of NFC that's usually not covered. I worked with it some 5 years ago before the COVID. I worked on a payment application, and from what I got, like if you go into the documentation, there are basically like 4 flavors of NFC available on Android. First one is most common one called NDEF, NFC Data Exchange Format. So it's a data format that's native to NFC. Is it working? Okay, amazing. So it's native to NFC, and there is really good support for it from the Android side. If you have a card that supports NDEF format, it has some data encoded in it. When you put it against your phone, Android will automatically read the data. It will read the type. It's encoded in MIME type. You can subscribe to different types. You can say, hey, I want to read cards, but only with URIs inside or with JSONs or something like that. There's a really good support, really good documentation on it. And I'm gonna be talking about it. It's like normal mode. You can do documentation. Android got your back. The second one is normal plus. It's MIFARE cards. They're essentially industry standard. They're extremely widespread. They're really old. There are a bunch of flavors of them. If you have a transport card, it's probably MIFARE. If you have an access card for your office building, it's also probably MIFARE. And Android has support for them as well. They don't really have documentation. You need to go into documentation for the specific cards to understand what's going on. But at least Android SDK has classes that will allow you to read these cards. Basically, on general level, they're pretty easy to work with. It's basically like a file. You can access it. You can just say, hey, read me data at this address. You get the data back. Newer cards support also authentication, support some additional modes. Android, of course, doesn't support that, but basic reading capabilities, you have it. And the next is called, Android calls it ISO DEP or DEP. I have no idea what this abbreviation means because the protocol that they refer to is called, Card and Security Devices for Personal Identification. How do you abbreviate it to DEP is beyond me, absolutely. There's basically no documentation on Android side, like the picture to the right, the stack that you can be using is your only reference. If you want to understand how it works, open your specifications, read them, and that's it. It says here that it works with 14.44.3, that's a transmission protocol, and that is how Android defines this class. But you will actually work with ISO 7816 on top of that, and I'm going to be using that. You can still use those 44.3 specification, but a different flavor of it, 43-3. And that is if you want to work with NFC cards, but without all the higher level logic. There are 4 flavors of NFC, of transmission protocol variations, NFC A, B, F, and V. I think A, B are mandatory, F, V are optional. By the way, MIFARE is optional too, not every device supports them. And that is a spare topic. If you work with that, tell me about it. I don't know anything about it. So we're done with that. And there's like one additional thing about this third flavor is ISO DP. Only for those codes you can work in 2 modes. First one is a regular reader mode. You have a card, you have a phone, you press the phone against the card, you read data from it, you set commas, you receive responses. There's an alternative mode called HCE, and that's, for example, how Google Pay works. In that mode, your phone emulates a card, and you can press it against a regular reader, like a payment terminal or access terminal or anything else. And in this mode, your phone processes commands and returns results. I'm not going to be covering NFC. I'm just mentioning that it's there, and they again have good documentation for setting it up, and as for protocol, I'm covering that as a part of reader tracker. Okay, you have a phone, you have a card. How do you make it work? First of all, you go into the manifest, as usual, and you declare an intent filter. This is like one way of doing it. You can also use NFC manager, NFC adapter, and subscribe directly, but there's also intent filter, and I want to be using that. You need to define the filter first. You're using tag discovered intent that will be dispatched when there's a card that's not NDEF and hasn't been handled. It will be dispatched with tag discovered intent. Second one, you need to define a tag filter. Android won't serve you all the cards that it sees, only those that match the tag filter that you declare in your application. Tag filter basically looks like that. It contains of tag lists, and each tag list is a combination of protocols you want your card to support, right? You can use basic NFC formats from A to F. There are two formats for NDEF cards. There are two MIFARE protocols, and this ISO DEP that we're going to be using. If you want to handle two different types of cards, you want NFC A with ISO DEP, for example, but you also want to handle MIFARE cards that are incompatible, you can add a second tag list, and if a card matches either of those, you'll get your intent. If there are multiple applications that want to receive those intents, Android will ask the user, and generally it's not advisable to do it, so try to narrow your list as much as you can. Okay, you've set it up, you received your intent, what you're gonna do with it. First of all, you of course check the action, maybe it's wrong intent, and if it's the right one, it will have a so-called tag inside. Tag is not really a card, it's more like a handle that allows you to check which card specifically did you get, which technology does support. And second, it will allow you to create an object that will use a tag as a handle and will allow you to run the commands against the card. So if we have the tag, we need to check the tag list. It's a field, and it contains Java qualified name of classes from the Android SDK that you can use with this tag. We insert in ISO DEP. Again, I'm saying that. We filter for that, and we create an instance. All right, that is essentially where Android stops holding our hand, because what you can do with card. First of all, you need to connect with it. You can't send commands unless you've connected. It's also closable, so it's very nice if you close it after you're done with it. I'm using use from Kotlin that will handle this for me. And then I have a method transif, and it takes a byte array and it gives you back a byte array. That's all the support you get from Android. Now you need to do things in your own. What you send is a comment, because we are in the reader mode, and card will return us a response. That's return from specifications response. Before I go into comments and how they look like, let me talk about the card itself. This specifically ISO 7816 talks about logical structure of the card. In terms of the specification, card is more like a computer. It has a sole file system, those Fs and MFs. It's not what you think it is, it's files. So you have like master files, you have elementary files that just contain data, and you have so-called dedicated files, DFs, that could be folders, it could be applications, it could be both, actually. And this protocol allows you to navigate this file system. It allows you to select files, get information from them, and if they're applications, you can run those applications. In this talk, I'm going to be using, as an example, payment flow for MasterCards. To do that, we need to first find the folder that contains our application. We need to select it, and then we need to run some commands against it to get some data. So first of all, how do we select a file? We use the command. The structure of a comment looks roughly like that. Comment consists of, first of all, it's a header. It describes what your comment is about. It has a class. A class helps two main purposes. First of all, it distinguishes between universal comments, so-called inter-industry, and those that are proprietary. For example, all the comments that are related to selecting files, they're common for all types of cards. Payment, transportation, doesn't matter. They use class 0. Payment cards use class 8 as a proprietary. Ins is a unique byte that describes what comment actually is. P2 and P1 and P2 are parameter bytes. They mean depends on the comment. Sometimes it's a parameter, sometimes it's a configuration bit mask that selects specific mode. You'll see an example of those, both of them. Then we have a body. Body has a size inside of it. It's either 1 byte or 3 bytes if 1 byte is too small for a payload, and the payload itself. The next part in the comment, by the way, it's called not just comment, it's called comment APDU. APDU is Application Processing Datagram Unit. You send APDU and you receive response APDU from the card. So the last byte in APDU is an indicator of how much data do you want to receive from the card in return. I'm using the value 0 here. I'm going to be using it everywhere. But 0 means unrestricted. You can also restrict it. You can skip the byte if I'm mistaken, and then it will be indications that you don't want any data in return at all. I'm going to be using 0 and not talking about it again. So we have a format. Now we just need to send the comment. For payment cards, there's like 2 specific names for files that contain payment applications. First one is one basis, DDF01. That's for contact cards, the ones that you insert into the card reader. For contactless cards, the one you press against the reader, it's 2 pay. If you get a specification that says 1 pay and they tell you to implement it with NFC, you have been handled the wrong specification, ask for another one. So we compose a comment. We compose a header. We use a select command. Its instruction is A4. We set P1 to 4, which means that we're using so-called dedicated file name because we want to select a dedicated file. And we put this dedicated file name as a byte array as a body. I didn't really mention it when I was talking about command structure, but I'm using unsigned types here. My notes is from Kotlin, so I'm using ubytes, ubyte arrays, and so on. By default, this protocol expects everything to be unsigned. If you're going to be using bytes, well, there might be issues with that. So within the byte array, we get a response. What does it look like? It's really easy. You have data, and last 2 bytes would be a status. So we check the status. Yeah, because before I go into the status about the data. Data can be of 2 types. First of all, it could be so-called primitive. It's just byte data, byte array. You are responsible for interpreting it according to your application. Second one is a universal format called BRTLV. Better is not Berlin, unfortunately. It's a binary format. TLV means tag, length, and value, and that describes the structure for it. Each record consists of a tag, a length that tells you how much data inside, and value. Value can be a primitive, or it could be another TLV object. The difference between BER TLV and simple TLV is that BER is self-descriptive. You don't need a schema to parse it. All the data that you need to understand if it's like a composite TLV or if it's a primitive, it's all syntax, it's all encoded in bit flags inside. It's also a format that's used in ISN1 protocol that's used for encrypting certificates. So your HTTPS works with BERTLV under the hood, and your certificate that you use to sign your applications using it too. I'm not going to go into specific structure. BERTLV is kind of complicated. I'll just point you towards 2 libraries that I've been using. Sorry, one I've been using, and the second ones they found. First one is a little bit awkward. It's not just a library, it's more like a validation tool that you can compile and run from the command line. It's not just for TLV, it's for payments in general. So it's a little bit bloated, to say the least. But on the other hand, it provides a lot of utilities for you. It has constant list from payment specifications. If you want to read specific tags, you don't need to encode them yourself, just pick from the list. It also has a descriptive database. For example, you can look up your tag and to tell you what is it about, its description, length, and so on. So for educational purposes, first library is great. If you want to use something in production, then maybe you can take first one, fork it, and just delete everything you don't need to, or you can use the second one. They're both a little bit old. First one is written in Kotlin, but it was written like 6 years ago, so no modern sugar. Second one is written in Java. Pick your poison. So let's pass our response. We got something from the card. First of all, we check for the status. If it's 9,000, which means SP OK, that means everything went well. We pass the response, and then we can basically work with it as with an object tree, right? We can take a look at the tag, for example, and print it to see what we got in response. We can use a tag and feed into this metadata object in the env tags class. I'll be talking about what env means a little bit later, but for now, most of the tags that we'll be using will be declared there in that class. And we're reading the full name. It will be description for the tag. Then we can check the TLV itself. Is it a primitive or a constructed? If it's a primitive, it only has a binary data. We can only print it because I don't know what to do with it. But if it's constructed, we can go iterate over each child and maybe print it again. If I run something like that on the data that I got from my card, I received something like that. So I received an object called FCI template. It's basically a decryption of a file. It contains the file name. Notice that it's the same stuff that I sent, which means I got the right file. And it has the data about the content of the file. What I'm interested in right now is tag61 application template. It tells us that inside of this file there is an application, and I can call it. It also has everything that I actually need to run. It's called ADF, application dedicated file name. Another name for it is AID, application identifier. And Android is using term AID. So if you read the documentation, you see AID, there's ADF actually. There's an application label. I'm using debit MasterCard, and there's a priority indicator for the terminal. If there are multiple applications, reader is expected to respect priority and pick applications starting from the lowest one. Okay, I have ADF. How do I select it? With another select, of course. It's the same command, A4, same P1, but this time I'm passing the application identifier. The response is a little bit more verbose. This time it tells me the preferred name for the application, the one that can be shown to the user. It also has this, where is it? 9F11, issue a code table index. It's a field that terminal can use to decide which char set to use to decode preferred name in case it's not in latent, in case it's localized. Terminal can actually process the data. There's a language preference. For me, it's English, priority indicator. And basically that's it. So just a little bit more information. But at this point, I have selected the application. I can send comments to it, and using those comments, I can get some more data. So we're basically done with main specification, like industry. Now I'm going to be talking about ENV. ENV is a term for, well, first of all, it's a consortium. ENV is a mix of Europay, MasterCard, and Visa. Europay is now MasterCard, so it's MV, in fact. They have 4 large specifications called ENV books that cover the whole process of performing payments. How do you do it? Which data forms do you use? Which cryptography do you use? And even I think the 4th book contains information about device itself that you've been using, requirements for keypads and card contents and whatnot. It's a proprietary specification, so common class is 80. And we're going to be using it to actually get some interesting data from our card. The payment process consists of 2 main steps. First one is we get data from our card for performing transaction. Like if you take a step back in time, like 70 years ago when cards were first introduced, the whole goal, like the business model for using plastic cards, was to let people buy stuff from television, from telemarketing, without sending checks. So that was like main point. And in this exchange, the role of the card is to provide an equivalent of a paper check. In this case, it'd be a send transaction, basically an electronic IOU that a vendor can give to their bank and receive money for them. So the process kind of mimics the check writing process. At first, we need to write the check itself, and then we need to sign it. That would be the second step. First step is handled by the reader itself. So to write the check, it needs data from the card. And for that, it uses the so-called get processing options command, code A8. You don't need any P flags. And data is essentially an empty common template TLV tag. So it's really no data at all. As a response, what I get is two important fields. First one is AIP, application interchange profile. It tells the modes that my card supports. In this case, it tells you that it can verify the card holder, me. Terminal is expected to perform risk management. That's on them. My card supports offline payment. If I'm flying on a plane and I want to buy some overpriced beer and there's no internet, my card can still pay for that, and this transaction will be verified after terminal comes online. Obviously, it comes with extra fraud, so some cards don't support it, some cards do. And I'm using EMV mode because, well, that's what I'm doing. The second important part is application file locator. The thing is, card doesn't give you all the information at once. Instead, it gives you a picture of the information that you're expected to parse and use to query data. Application file locator, if you want to parse it, is a combination of 4-byte chunks. Each chunk encodes in first byte the so-called SFI, simple file index, 2 record IDs, where to start, where to end in that file, and the third one tells you if you are doing offline notification, how many records from that file you are expected to include. I'm going to be ignoring the last one because I'm not doing offline notification, but I would really like to read all these records. How do I do it? Believe it or not, with read record command. It's a little bit tricky to use. As I said, sometimes you can use P1s for data, and that's precisely what I'm doing. So SFI is only 5 bits long. So when I initially parse the file record, I take the 5 most significant bits, shrink it right, so I get my value. When I put it into P2, it should be in the 5 most important bits, and the 3 last bits are used for configuring how this command works. In this case, I'm setting the third bit to last to 1 to indicate that I want to read only one record, the one that I'm supplying in parameter P1. So I need to take each file, iterate over each record, and pull everything that my file gives me. In my case, a file is relatively short. It's like 3 files to work with, 3 groups of 4 bytes. Most of the data I'm not going to show you because it's like keys and private info. There are a lot of information related to the issuers, certificates, like you have a card, open key, issuer, bank keys, like a lot of cryptography that terminal will need to verify the transaction and to perform online notification and offline one. But for me, the most interesting record was the first one that I received, and it actually contains all the data about my card, all the data that I can see on my card on the front page. For example, it contains expiry and pen. I removed them for obvious reasons, the card number. It has application effective date, is the date from which your card is active. If you try to pay before the active date, you will get automatic decline. Notice that all the data that I'm showing, like in application currency code, in country, in expiry, it's actually in hexadecimal. I didn't convert anything to decimal. So if you decide to take, for example, effective date and take the first byte and say it's going to be here and then just use it as a byte, then the actual number that you will get in decimal would be like 36. So it will be a little bit off. Don't do it. I would say the safest way to work with those fields is just convert them to string and then just go from there. Strings for the win. So I have currency code is euro. I have a country code is Germany. I have two CDOLs objects that focus risk management. The previous step told that terminal expected to perform that. They're going to use CDOLs. And it also has a nice field called CVM list. It tells reader how it can verify that I'm a legitimate holder of the card. First option, the preferred one, is PIN. If PIN is unavailable, because PIN should be verified online, I can sign my check. Or there's also a no CVM option. No CVM means basically that we don't need to verify. For example, if you're just buying a donor, it's €6, your card doesn't care. So that's called no CVM, and generally the decision if it will be no CVM or not lies on the card. So card can compare it against some thresholds or order history and decide that, okay, this transaction it needs verification, that one doesn't. So another really interesting field to me, it's track 2 equivalent data, 57. I cut it again. It contains PAN and the expiry date. And what's interesting about that card, about that field, is that it's legacy. It's ancient legacy from, I don't know, 60s, 70s, when people first came up with the idea of magnetic mark strips on cards. And again, the use case was let's enable people to pay quickly in shops with our cards, without checks. So let's just encode all the data so they couldn't swipe and they didn't need to dictate the card numbers or whatever. Just let's make it easy. And the equipment that you needed to encode this magnetic strip cost an obscene amount of money, it took obscene amount of place. Nobody even could imagine that 10 years later, a clone kit would cost, I don't know, like $400. Every teenager could afford one. So this turned out to be a huge security issue, and that what actually prompted people to move to smart cards that don't have possibility to clone the whole card. But you couldn't just switch everything. You still needed to support all those legacy processing systems, all those banking systems. And what they did, they just took one of 3 tracks from the magnetic strip and put them into card data. So it's been, I don't know, like 40 years since people understood that magnetic strip is completely unsecure, and we are still using track 2 equivalent data in payments, even for NFC. So there's like one step left. I'm going to go into details about it. It's a bit complicated. It's called generate application cryptogram. Okay, we prepared our check. We want to sign it. To do that, reader prepares a request and sends it to the card with this generate application cryptogram command. It can be run in 2 steps. First one is when card decides if it wants to perform offline authentication. If there's no risk, great, then the card will return so-called transaction certificate, and we're done here. If not, then the card can request online authentication with an object called IRQC. In that case, reader performs this online authentication, and then it runs generate application cryptogram again with the data it received from the processing. Alternatively, in both steps, card can just decline and return so-called IEC, application authentication cryptogram. It's a cryptogram, but it basically says no. Computer sagt nicht. And basically that's it. That's like a basic MasterCard flow. Sometimes for some payment systems, some commands might be different. For example, the one that I worked with, it didn't have generate application cryptogram. Instead, they use their own proprietary command that collapsed both steps into one. So you don't need to go forward and backward. Or it's more secure, I don't know. But that was their decision. Another thing is, like I was talking about, this is the payment process, but generally it's not restricted to money, right? You can verify anything. And another system that I worked with used the classic env flow with generate application cryptogram for building access. Same flow, okay, just now you're not verifying payments, you're just verifying access to the building. Same logic still. Now, what could go wrong with this whole flow, and how can it maybe between paid? I have a question for you. Let's say I'm parsing the comments that I've been sending. I already parsed the comment itself, class, instructions, p bytes. Let's say I'm definitely sure that size is within 1 byte, so I don't need 3 bytes for that. I'm reading the size. And what next I'm trying to do is I want to read size bytes from the next position. Indexes are fine. It's 4, it's 5, no errors here. But still, there's a bug in this code. What do you think it is? Okay, let me give you a hint. Yes, please.
Index out of bounds or something?
No, that's not an extent of bounds.
What happens when you call plus?
Hmm?
What happens is it the addition, it becomes signed?
Close. Expand on that. Okay. Java doesn't support unsigned data, right? By default, everything is signed. But 80 has a bit, is the most significant bit. It has a 0, 1, which means it's a negative number. So you would expect that it would be 128, but because we are working with bytes, like vanilla bytes, it's actually minus 128. You're trying to read negative amount of bytes. And since I'm using ranges here, ranges, I think, don't throw. They just return an empty range. Now I get myself an empty payload. Good luck debugging it. And speaking of, okay, not speaking about debugging, it'll be later. The second one is NFC is really weak. Like it's energy efficient communication protocol. Android phones are generally, they don't pump a lot of power. Okay. I just realized that you don't see lines there. There are like lines that connect another lines, and okay, this image doesn't make sense anymore. So what I was talking about, that phones on their own, they don't have much power in the readers. If you have a phone with a metallic back, you'll have problems reading cards. If you're using bumper, you'll have even more problems. On the other hand, it's not that much of a problem if you are writing a reader application, because you can always ask a user to like wiggle card a little bit and try again, and usually they can do it. Physical readers, on the other hand, they're usually a little bit more powerful, but on the other hand, they have no idea what is going on generally. So for a lot of them, if something goes wrong, the modus operandi is just try again. It didn't work, try again. It didn't work, try again. You would kind of expect that a reader would respect the whole flow and go through all the steps one by one, and if something goes wrong, maybe it will restart from the beginning, but no. It will just, that's like an example of what could happen. It selects first file, selects second one, it doesn't like something, and then it goes back and selects another folder. Like you don't expect it, but it happens. Sometimes it's not even nice like that. It could go switching between different IEs. It could go switching between different pay environments. And to make things like even more painful, remember that select comments are the same. They don't differentiate between like first step and second. It's the same comment, same bytes, same parameters. It's just the payload is slightly different. So every time you receive a comment, you need to match it against your IEs, your dedicated file names, and God forbid if you support multiples in your application. Good luck with that. Another issue that could happen, and it happened for me with non-payment cards. It was a non-payment card, right? So there's no money involved. So technically, there's no harm done if you repeat the transaction, right? So what the reader did is that they just looped through the whole flow as long as there was a card in the field. It didn't matter if it was a failure or if it was a success. So when we were writing the application, we can't expect that there will be multiple errors. So we added some throttling, and we didn't immediately show error messages to the user, but nobody ever expected that you could get 20 successes per second. And we had a really nice screen with animations, and I think it was a bit of vibration and maybe even sound, like voiceover, telling you, hey, success. And then we tried to launch the screen 20 times per second, and it was horrible. I didn't enjoy it one bit. So be aware, like devices in general don't really have much respect for specification. If it works with cars, then it works with cars. I mean, it's devices, they've been deployed. Nobody's gonna travel throughout Europe and collect devices just to flash them because you found the bug. Not happening. And that moves us to the last pane, and it's logging. So first of all, the whole scenario would be for your application that people are going to be using it outside usually, not at home, not at work, like in shops and I don't know, fuel stations in the middle of nowhere in some village in Alps, I don't know. And they really want it to work. They're not going to stop for a moment and say, okay, there's like some sort of error, let me press a button that says send report to the developer. They'll just be upset, right? And debugging it is also really complicated. You're working with binary formats. If you parse something wrong, it's really hard to understand what exactly happened, right? Why is everything happening not as you expect it to be? On top of that, sometimes you use cryptography, sometimes you do a lot of it. Again, it's really hard to understand why suddenly your reader rejects your transaction, says that signature is incorrect. Like, it's correct for my device. Why can't you be normal? But on the other hand, if you are working with sensitive applications like payments, there are a lot of regulations that basically forbid you from logging everything and, God forbid, sending it to Firebase. It's really tempting to just record every transaction, but it's not allowed. You can do it. And it's like a balance. You want to log as much as you want, but on the other hand, you can't. So the solutions here is still log, but try to sanitize your logs. For example, you can't log the whole TLV response, but maybe you can log the structure, you can log which tags you have arrived, what were the lengths that you have parsed. Maybe even from that, you can deduce something and compare and say, okay, there's no like tags that I'm expecting, or the size is wrong, maybe I parsed data in the wrong way. It's painful. If you have problems, maybe talk to your IT security people who are going to be responsible for your application. Maybe you can figure out something. But generally, it's going to be like the biggest problem. My application doesn't work in the middle of nowhere. Please debug, please fix. And it probably doesn't work because they're using some old readers that actually has some bugs. Good luck. Helpful stuff. To the right is the link to this presentation. There would be a link to the demo app. There will be a repository on GitHub that you can use, install, and use against your Mastercard cards if you want to. And there are 2 links to online tools that help with, basically with data from the payment process. The first one has a lot of decoding tools, especially for things like those complex fields like verification method lists or anything else. You can take data from text, put it in, and it will decode it for you. It also allows you to parse the basic TLV methods. The second one is just about TLVs, but it also has a really handy database of all the tags. If you have a tag and you don't know what it is, you put it inside and it tells you what it is, what size is expected, what specification does it come from. That's it. Thanks for coming. Any questions?